So let's look again in the simple case when we've got one variable, one x. Again, we're going to get a bit more mathy now. This is the form, the mathematical form of the Gaussian density function for class K when you've got a single x. So there's some constants over here. The important part that depends on x is in this exponential form over here. And we see there's a mu sub k, which is the mean for the observations in class K, or the population mean in class K, and sigma sub k is the variance for that variable in class K. Now, in the first instance, we're going to assume that the variance, sigma sub k, is actually just sigma, the same in each of the classes. Now, that's a convenience. It turns out it's an important convenience, and it's going to determine whether the discriminant function that we get, the discriminant analysis gives us linear functions or quadratic functions. So if we plug into Bayes' formula, the formula we had on 2 slides back, we get a rather complicated expression. So we've just plugged in the form of the density in the numerator, and there's the sum over the classes in the denominator. And it looks pretty nasty. Well, luckily there's some simplifications and cancellations. Now, we get this because to classify an observation to a class, we don't need to necessarily evaluate the probabilities. We just need to see which is the largest. So if we take logs, whenever you see exponentials, the first thing you want to do is take logs. And if we discard terms that do not depend on k, then we so that amounts to doing a lot of cancellation of things, of terms that don't count. This is equivalent to assigning to the class with the largest discriminant score. And so that complicated expression boils down to a much simpler expression over here. And notice it involves x, our single variable in this case, and then it involves the mean and variance for the distribution, and it involves the prior. Okay? And importantly in this case, this is a linear function of x. So there's a single coefficient for x, there's a constant, and then there's a constant term, which consists of these two pieces over here. Okay? And so we get one of those functions for each of the classes. If there are 2 classes, you can simplify even further. And let's suppose now that the probability of class 1 is equal to the probability of class 2, which is 0.05. Then you can see in this case that the decision boundary is exactly at mu1 plus mu2 over 2. So it's back to this picture in the previous slide. In this case, the priors were equal. These are actually 2 Gaussian distributions. And the decision boundary here is at 0. In this case, the 2 means were exactly the equal amount on the opposite side of 0, so the average is at 0. So intuitively, that's the right value for the decision boundary, which is the point at which we classify to one class, the boundary at which we switch from classifying to one class versus the other. Now, it's not that hard to show, so see if you can show that. You basically use this expression for each of the 2 classes and look to see when it's the one's bigger than the other. Not that hard to do.
I'm confused. There was a square term in the previous expression and it's gone.
Oh, Rob, are you causing trouble here again? I was hoping to avoid that nasty bit. Rob's right. What if you expand out this square term here, there's going to be an x squared. But, you know, there's an x squared in the numerator, and there's x squareds in each of the terms in the denominator, and there's no coefficients in front of that x squared that's specific to a class. So that's one of the things that cancel out in this ratio. You knew that, didn't you, Rob?
Oh, yes.
Rob knew that. All right. So this is with populations. What happens if we have data? We can't draw nice density functions like we've done over here, but we just estimate them. So here's a picture where we've actually got data. So we've drawn histograms instead of density functions. Now what we do is we need to estimate for the Gaussian rule, we need to estimate the means in the 2 populations and the common standard deviation. Well, in this case, the means, the true means are minus 1.5 and 1.5, which means the average mean is 0, and the probabilities were 0.05. But we don't know these, so we're going to estimate them from the observed data and then plug them into the rule. So this is how we estimate them. The priors we need to estimate, so that's just the number in each class divided by the total number. That's obvious. The means in each class, we just compute the sample mean in each of the classes. This is a tricky little notation here. This says 1 over nk, that's the number in class k. And this is a sum over I such that yi is equal to k. So yi is recorded in the class label. So this will just sum those xi's that are in class k. And clearly that's the right thing to do to get the sample mean. The sigma square is a little trickier. We assume the variance is the same in each of the classes. And so this is a formula. It's called the pooled variance estimate. So we subtract from each xi the mean for its class. So this is what we do if we were computing the variance in class k. But we sum all those square differences, and we sum them over all the classes, and then divide it by n minus k. So if that doesn't make too much sense, another way of writing that is in this form over here, which says we estimate the sample variance separately in each of the classes, and then we average them using this formula over here. So this is just like a weight on each of those variances, and that weight's to do with how many observations were in that class relative to the total number of observations. And then the -1 and the minus k, that's a detailed, and it's to do with how many parameters we've estimated for each of these estimates. There's one parameter, it's the mean. Rob's falling asleep.
Sorry.
Too much detail,
Yeah,
Rob?
exactly.
Way too much detail. Okay. So there we have it. Those are the formulas. You plug those back in, you'll now get estimated decision boundary. And instead of being exactly 0, in this case, it's slightly to the left of 0, but pretty close.